mean free path. So molecules are traveling in straight lines till they run into each other. Well, how far do they travel before they run into each other? Well, some are going to go a long ways and some are going to go a very short ways. It depends on traffic, basically. So they don't all have the same distance that they travel between collisions, so we have to look at an average. So the average distance that a gas particle will travel without running into anything is called the mean free path. Mean meaning average. Free path, so how far can it go without running into stuff? That mean free path will decrease as the pressure increases. So I think of, increasing pressure, that's pushing the molecules closer together, right? Decreasing the volume will increase the pressure. It's more crowded. They're going to bump into each other more frequently. Just to give you some context here, if a nitrogen molecule was the size of a golf ball, it would travel about 40 feet before it runs into anything, either another nitrogen golf ball or the wall of the container. But if you increase the pressure, then the mean free path goes down. It'll be less than 40 feet. Diffusion and effusion are processes where gases are spreading out. We know that gases will expand to fill their containers, and the way they do that is through these processes. So if you have gas molecules that are spreading from a high concentration to a lower concentration, this is called diffusion. And this happens because the gas particle starts moving, and it's just going to keep traveling in a straight line till it bumps into something. So remember, we dissolved the copper wire in a beaker, right? And we saw this brown gas form, and it mostly came up, and then it just kind of dissipated, right? So you think about those gas molecules that are being formed, the ones that are headed straight up, they're going to go straight up out of that beaker till they run into something. They could run into an oxygen molecule in the air, or they could possibly even go all the way up and just hit the ceiling of the hood. Some of them may bump into each other down in the beaker still and crash back down, but eventually they're all just going to spread out. That's diffusion. Higher concentration going to a lower concentration. Gases will escape through small holes. So if you've got a balloon and it's got a little tiny hole in it, we know from experience that that balloon's going to go flat, right? Because the gas escapes. When we have a gas escaping through a small hole into a vacuum, this is called effusion. So the rates of diffusion and effusion are both related to the average velocity of the particles. The average velocity does depend on the identity of the gas. The average kinetic energy is the same regardless of what kind of gas you have in the container, but the velocity is different. Heavier particles move slower, lighter particles move faster. So for gases at the same temperature, the rate of gas movement will be inversely proportional to the square root of its molar mass. Wait a minute, do we have that? No, I don't want to do that yet. So we looked at this equation. Root means square, velocity. I left out the R. 3RT over the molar mass. So the rate of gas movement has to do with the velocity. And here, if we're at the same temperature, the temperature is the same, R is the same, the 3 is the 3. It's divided by the molar mass, and it's the square root. So the velocity is inversely proportional to the square root of the molar mass. So larger particles, if the particle is twice as large the speed doesn't go down by a factor of 2, it goes down by a factor of the square root of 2. So Graham's law of effusion. Remember, effusion is a gas escaping through a small hole into a vacuum. So here we have an illustration of effusion. We have 2 containers here, 2 boxes next to each other. Initially on this side we have gas, and on this side we have a vacuum. No gas particles. There's a small hole here that's large enough for the gas molecules to go through. So here we have gas molecules traveling in straight lines until they run into something. So how can they get into the other container, the other side? They're going to bounce around in here until they hit a path that hits directly through that hole. If they hit directly through the hole, they'll go through. Otherwise, they're just bouncing around. Does that make sense?
Can they go back though?
They could go back, yes. But they are unlikely to do that. So we think about, well, what would affect how frequently a gas particle happens to hit the hole? Temperature. Because at higher temperatures, the particles are moving faster, right? So with them bouncing around faster, we're going to get more of them getting through the hole. So which kinds of particles at the same temperature move faster? Heavy ones or slow ones? Heavy ones or light ones? The light ones move faster. Think about the football players. The light ones move faster, the heavier ones move slower. So how fast a gas effuses, escapes through this little hole, depends on the molar mass, the mass of the particles. Okay. So we can take the root mean square equation, root mean square velocity equals the square root of 3RT over the molar mass, and combine that for 2 different gases, gas A and gas B, and so we can compare the rate of effusion of 2 gases. So the rate of A is inversely proportional to the square root of its molar mass, and the rate for B is inversely proportional to the square root of its molar mass. So if we know the molar masses and we know the rate of one, we can find the rate of the other. Any questions? Find the ratio of effusion rates of hydrogen gas and krypton gas. Rate of effusion, how fast it would escape through a hole into a vacuum. Before I get started on that, let's think about why the particles are not going to go back through the hole. How many particles do you have over here? 3. And we've got a lot more than 3 over there, right? So if there's a vacuum over here, there's very few particles. We've just started effusing, there's very few particles. What are the chances that this particle is going to hit a trajectory that's going to go straight back through the hole? Very, very small, right? Very small. Now, as this process goes on and more gas molecules effuse, then the chances of these getting back the other way increases. But the rate of effusion is into a vacuum. And so if you let this go on very long, this isn't a vacuum anymore, and then you're not going to be talking about the rate of effusion. Does that help? So ratio of effusion rates. Well, we need that equation that we just looked at. So the rate for A, instead of A, let's use hydrogen because it's first in the problem. The rate of effusion for hydrogen divided by the rate of effusion for krypton. That would be the ratio of the rates, right? That's going to equal the square root of the ratio of their molar masses. But it's not hydrogen on top. Hydrogen's on the bottom. Because the bigger the molecule, the slower it effuses. So this is H2, and that's krypton. When we were calculating root mean square velocity, these molar masses had to be in kilograms per mole. Is it going to matter if they're in kilograms or grams here? No, because the units are going to cancel out. Right? So if we had kilograms per mole divided by kilograms per mole, those units are going to cancel out. If we do it in grams per mole, the units are also going to cancel out. So, if you want to convert them to kilograms, you go right ahead, but you don't actually have to because the units are going to cancel out. So we need the molar mass of krypton, 83.80. So 83.80 grams per mole. And the molar mass of hydrogen, and then we have to take the square root of that. Oh, I just messed it up. I'm getting 6.44728. What are the units on that? It's a ratio, there's no units. Because I wrote my molar masses with 4 significant figures, I can have 4 significant figures here, and I'm going to say the ratio is 6.447. And you're like, well, that doesn't look like a ratio. Well, 6.447 to 1. All right, there's a ratio. So hydrogen gas will effuse, escape through that hole, almost 6.5 times faster than krypton will. Any questions? So we know that balloons don't stay inflated forever, right? Typical latex balloon, you fill it with helium, you have a party, it's all great, and the next day it's just not as buoyant as it was, and by the following day that balloon's definitely going to be just sitting on the floor. Why? What happened to the helium? Did it wear out? No, it escaped. The latex has little tiny holes. Those holes are big enough for helium atoms to get through. Why don't they just all go through to start with? Because they're zinging around in straight lines, and in order to escape, they have to hit a hole dead on. Otherwise, they're just going to be bouncing around. So what if you have a balloon full of air and a balloon full of helium? Now, the air balloon can be fun, but it's not as fun as the helium one because it doesn't float, right? Which one do you think would go flat faster? The helium one. Because the particles are smaller. And it's not that it's easier for them to fit through the holes, it's that they're moving faster at the same temperature. Air is mostly nitrogen, molar mass of 28, oxygen, molar mass of 32. Those are much more massive particles than helium with a molar mass of 4. The helium particles at the same temperature are traveling on average a lot faster, and so they will escape through the holes. I like balloons.